All right, so last video, gosh, I'm a bit flustered now with this being in this room for actually the entire morning. And I hope you are fine looking at this video tomorrow morning. I'll post it later in the afternoon for you. Okay, so it leaves us with the last bit, is integrating processes. So I told you that a first order process is described with a first order differential equation in the following format: tau dy over dt plus y equals to kpu. Okay, so that's the first order differential equation, but something else happens if the factor of this y here isn't there. Then it's no longer what we call a first order process. Okay, let me explain. Think about an integrating process. So this is not an integrating process. Let me cross this out. So this is, we've done with that previous video. Move on, next video. Okay, so we have a tank with a liquid inside the tank, an inflow. We call the inflow rate Qi, and the outflow rate we call Q. And it's a nice vertical container. So this could be your wash basin, only that it has an area A here, and it has a height H that is the same over the entire height. So if you would have a conical container, it would be a different process, right? So we have the same area for the entire height of the container. Okay. And we can describe the dynamic behavior of this process as follows. First of all, we have to figure out what's our input variable. You can pause the video and think about it. What's the input and the output of the system? Okay. Okay, enough pausing. The input to our signal is our flow rate. And we have to decide which one, the inflow or the outflow. For the purpose of this example, we're going to pretend that the outflow rate is constant. We're not changing that. And it's for example, 0. We pretend it's 0. It could be a different value. The most important thing is assumed to be constant. Okay. So the input to our process is our flow rate Qi that can change. So think about it as a bathtub that you're filling or not filling. Okay, by changing the inflow rate, you will make sure that the level changes. So our output variable as a result is our level H. Okay, and we call this the tank. And the relationship between the level and the flow rate is as follows. It's the volume, or the change in volume. The change in volume changes only the height because the square area doesn't change. So it's A times dH over dt. And that is the inflow rate minus the outflow rate. What goes in goes out. Okay. So that is our differential equation. So we have our input, U of S, the inflow rate, and the output, Y of S, is the height or the volume in the container. So we can do the Laplace transform of this equation, and we get A times S times H of S equals to, we pretend this one here is 0. We pretend doesn't exist for the purpose right now, because the reason why we do that is because we can only think of single input, single output systems. If you were to have a second input, it would be a two input, one output system, and we can't do that for the purpose of this course. Now, there are ways of dealing with this, but we're not going to do that. We just assume for the purpose of this course that this outflow rate is 0, and we end up with our flow rate Qi of S as the input signal. So now let's write this slightly differently. We can write A times S, and we're going to use the naming that we have generically, right? This is our input and our output. And we would like to know what is the output as a function of the inputs. So y of s equals to 1 divided by as u of s. Okay, right. So what does it look like? We call this here the transfer function g of s. And you can see it's sort of a first order system because it has a first order differential equation, but it's not a first order process. We call this an integrating process. Why? Because it only has the integration of the input. We could write this slightly differently. We could write this even before we move into the frequency domain. We could write this as a times h equals to the integral of qi, if you would like to have it like this. So we're integrating the flow rate over time, and the height of the liquid in our tank is determined by how much we've put in. Yeah. And so this is what an integrating process looks like. It has the transfer function, a constant 1 over a, but more importantly, it has the form 1 divided by s. Okay. Now you can say, I'm not confused now because I had a signal. The signal was 1 of t, and it corresponded to 1 over s. And now the transfer function is also 1 over s. So at this point in time, you have to be super careful because, yes, this is a system, but it's not a signal, all right? And it has the same form. It's 1 over s, and this is 1 over s, but we're not doing the inverse Laplace transform of that signal on its own, of that system on its own. We can do the inverse Laplace transform of, for example, the step response. So if you wanted to do the inverse Laplace transform for our y of t. So let's think about this. What does the step response of an integrating process look like? All right, so it's the same thing. I had this on this side here earlier. What do we do? This is our input signal. This is our output signal. And we put in the unit step. So you can figure out yourself without even doing any maths. You can figure out what the output is going to be. What happens? You have a bathtub, it's empty. You open the tab. How does the level of inside the bathtub change? Think about it. Okay, but this is, and then you can draw it. Right. But we're going to do, because we can, we're going to do the maths behind that. So we're going to do that. And what do? We take our system here that is described with this transfer function. We say u of s equals to 1 over s, because we're putting a unit step in there. And then let's see what happens to our output. Our output is 1 divided by a times 1 divided by s squared. Okay, so now we have the square function of s. And for that, I gave you the lookup table in the first video when we looked, I think it was the first video. Yeah, we had a function that I said sometimes it's an input, sometimes it's an output. It was the ramp function. And the inverse Laplace transform of, the Laplace transform of a ramp function is 1 divided by f squared. Okay. So you make the use of that fact, and we say why we do the inverse Laplace transform via this lookup table. Again, this is not really a table, it just has 2 entries. And we can write that y of t equals 1 divided by a r of t, the ramp function. And r of t was defined as t for t is greater than 0 and 0 else before. Okay. So what does it look like? 0 because it's 0 before then. And then it is an increasing function that increases with the slope of t, almost, because we have a factor 1 over a. So it's got the slope 1 divided by a. Okay, so for each step I do to the right, I do 1 divided by a upwards. Okay, so that means if my area is larger, 1 over a is going to be smaller, the slope will be slower. So the bigger my bathtub is, or the bigger my tank is, the longer it will take for this value here, y of t, which is the level, to rise. So my level will rise. Will it ever stop rising? It won't. Yeah, it's going to carry on ad infinitum forever and ever and ever, because it's called what we call an unstable process. Okay, so what do we know about an integrating process? We have the differential equation, which is dy over dt times a factor, let's call the factor k, and that equals to our input signal. Yeah, we have the transfer function that looks g of s for an integrator is k divided by 1 over k. Let's call this 1 over k over s. Main thing is it's 1 divided by s. This is our integrator. Don't confuse it with a signal. We can't do the inverse Laplace transform of a transfer function. We can only do the inverse Laplace transform of a signal. And our signal is y of s. So the step response of an integrating process is r over t. Equals to k times t for t is greater than 0, 0 for t is smaller than 0. Okay. We can think, you can try out here, you can think about yourself, what would be the impulse response? So this is when u of t equals to delta of t. What happens then? I fill the bathtub for a very short amount of time, but infinite, with an area of 1. What does y of t look like? For a delta, for a step. So sorry, this gives us y of t. What does it look like? Pause, think, carry on playing the video, and I will tell you. So y of t is going to look like this. It's going to be a step. Yeah, because I'm going to fill this. Think about it, I'm going to fill this a little bit, and then I stop filling it. Okay, so my impulse pulse is going to look like that. It's going to fill it for a bit. I stop filling it. So it actually is going to fill up, integrating, and it's going to stop. And if I make this pulse infinitely small and infinitely high, this curve here will, this linear slope will become steeper and steeper until it looks like a unit step. Okay, and this is what you need to know about an integrating process. I hope you enjoyed the videos for today, and next week I'll see you again in person.